Hi everybody, my name is Alex. I'm going to be talking to you today about how operating systems implement processor scheduling. Before we even start looking at what processor scheduling is, we're going to first go over what an operating system actually is. So we all at the very least have a basic understanding about what an OS is. If you have Mac OS or Windows, it's something that's going to change the overall look and feel of your computer. And while that's definitely true, operating systems are doing a lot more for us sort of behind the scenes or under the hood of our computer. Whenever we do just about anything on our computer, we're going to be interacting with an application. In order for that app to run, it's going to need to get some sort of resources from the hardware. Rather than just going straight to the hardware, the app is going to need to first go through our OS. This is to make sure that our app isn't going to do anything sort of malicious to our hardware or just use up too many resources so other apps can't run. So whenever an app needs to run, it'll first make a request to the OS. The OS will then check to make sure the request is all good. It'll get the resources for it and return it to the application. So one of the most valuable resources that our computers have are its processors, which essentially process things. Whenever an application needs to run, it'll at some point need to be put onto the processor, and then the processor can start executing basic instructions, and those instructions are going to make our computer actually do something. So pretty much anything that a processor does in our computer can be abstracted out to this idea of a thread. And a thread is just sort of this very abstract look at any sort of task that your computer can be doing. Threads are able to run concurrently or asynchronously of one another as long as they're put onto separate processors. So ideally, we're going to try and spread out our threads across as many processors as possible, so that way we can have many things running at the same time. So as programmers, we typically are viewing the programmer abstraction. We don't really think about how many threads we're running, how many processors we have available. That doesn't really matter to us. We just write code, execute it, everything's awesome. But the reality of it is our computers only have so many processors, so not all of our threads or all of our programs can be running at the exact same time. But unless you're running something crazy intense on your computer, you're probably not going to notice that not everything's running at the same time. And this is because our operating systems are taking care of that for us through processor scheduling. The operating system is going to use some sort of clever algorithm to put threads or to cycle threads on and off of processors in such an efficient way that we can't even tell that they're not running on the processor the entire time. So how does the operating system actually do this? I'm going to be walking you through a couple of different possible algorithms that an operating system could be using, and we're going to see how those algorithms can actually be combined together by an operating system to just make everything work. So the first one is very simple to understand, just FIFO, first in, first out. When a thread needs to be put onto a processor, it gets added to a queue. When it reaches the front of the queue, it gets put on the processor. It'll run on the processor till it's done, and then it'll leave the system, and the next thread from the queue can be put on. This is a pretty good algorithm. It's simple, very easy to understand, not a lot of room for error if you try to implement it, but it can be very inefficient. If the first thread to arrive at a processor, say, is going to take 20, 30 milliseconds to run to completion, and then while that's running, a whole bunch of threads that'll just take 1 millisecond to run arrive after it, it would make a lot more sense just to process those shorter threads, get them out of the way, but we can't really do that with FIFO because we're stuck waiting for that really long thread to run. So to fix that problem, we have shortest job first, or SJF. And so what shortest job first is going to do, it's always going to process the shortest job available, even if that means kicking off a longer thread that's currently running on the processor, which you can kind of get an idea from with the little meme at the bottom. So this fixes the problem that FIFO brought up where short threads could be stuck behind long threads. But now we pretty much run to the opposite problem. If we have a long thread that's waiting to run and a whole bunch of short threads keep coming in front of it, it's just never going to run. And another problem is that it's actually kind of impossible to implement it perfectly. Until that thread actually runs, we don't know exactly how long it's going to take to run. There are implementations where you try to make estimates based on past thread performance, but none of them are completely perfect, so it's not an ideal solution. So we have FIFO and shortest job first, which are kind of on opposite sides of the spectrum. They pretty much do the opposite thing, but they both share one commonality, which is their biggest flaw, and that is starvation. And as you can probably tell from all the frightened dogs around it, we don't want starvation. It's a very bad thing. So in operating systems, starvation refers to the indefinite postponement of an operation because a thread can't get the resource it needs. And what that means is starvation is just a thread can't run because it can't get on the processor. We saw this with FIFO because short threads got stuck behind long threads, and the opposite happened with shortest job first. So to fix this problem of starvation, we have the round-robin approach. And how this works is a thread gets put onto the processor. It runs onto that processor for a specified amount of time, say like 10 milliseconds. After 10 milliseconds, it gets kicked off the processor. A new thread comes on, runs for the same amount of time, and we sort of just cycle threads on and off the processor continuously until that thread is done. So now we don't need to worry about starvation anymore because all of our threads are going to be getting equal access to the processor, so everything's going to eventually finish. But round robin is even more inefficient than FIFO or shortest job first because now everything is just getting very limited access to the processor, and it's just going to take everything a really long time to finish. So if you were using an operating system that actually implemented round robin, it would be pretty obvious to you that things are running extremely slowly, not everything's going on concurrently, and it would just cause a lot of problems for the user. So we have these three algorithms, FIFO, round robin, and shortest job first. And it's pretty clear that none of these are really good enough for our computers. They're slow and efficient, some of them have starvation problems, but what we can do is take the unique benefits of all three of these and combine them into one sort of super algorithm, which is called the multi-level feedback queue. And all that is just a bunch of round-robin queues stacked on top of each other. When a thread needs to be put on the processor, it'll come into the top round-robin queue. It'll get put on the processor for that specified amount of time, like it would with a normal round-robin queue. Then it gets kicked off, and it moves down to the lower level round-robin queue, gets put onto the processor again, this time for a longer amount of time. And threads will just keep moving down and down and down this sort of stack of queues. And if it ever happens to reach the bottom queue, typically it'll be a normal FIFO queue. But ideally, the thread would finish running anyway before it reached that point, and then it'll just be kicked out of the system altogether. So the MFQ approach is taking advantage of all the three algorithms that we've already looked at. It takes advantage of shortest job first because short jobs are going to be able to just come to the top level, finish running on the first round robin queue, then leave the system immediately. Uses round robin because we don't have to worry about starvation because we're literally just using a bunch of round robin queues, so everybody's going to have access to the processor, everything's going to run, and it uses FIFO by literally just sticking in a FIFO queue at the bottom. So all the three main operating systems, Windows, Mac, and Linux, are actually using some sort of implementation of the multi-level feedback queue behind the scenes of our computers. So the next time you're running a whole bunch of applications at once, running some code, Spotify, whatever else you're doing, you can thank the MFQ in the background that you're able to do so seamlessly. Thank you.